Hello, this is my presentation on Lab 3 Planetary Motion. So the purpose of this lab is to use code to simulate the motion of celestial bodies. And some of the principles we used was the Newton's second law and the conservation of momentum. And so as for the preview, you knew the relationship of parallel and perpendicular change in momentum. And using that, we could find the mass of the black hole, which was found to be 7.74 times 10 to the 43rd. And then in part two, I found that a figure-8 orbit was unattainable for me, but that a velocity of 25,000, 0 was sufficient to not have the rocket crash. As for the equations and explanations, we use Newton's second law, which is F equals ma, and you can also have it as the change momentum. And this was used to calculate forces and such. And the main force that was here was the force of gravity, which is Fg is equal to g m1 m2 over r squared. And then we use the velocity update equation to change the velocity. And then we have the position update equation to change the position. So the models and assumptions, this is some of the basic code that we used, and some of the assumptions include that the objects were perfectly round and that there aren't other celestial bodies imposing gravitational forces in the system. As for the system and surroundings, in part one, the system is the black hole and the surroundings the planets. And in part two, the system is the spaceship and the surroundings are the planet and the moon. As for the initial conditions, we start off with the base code. And in part one, the black hole is at the origin, doesn't move. And in part two, the planet is centered at the origin. And the moon starts off orbiting the planet. As for details of experiment in part one, we use the code to calculate the distance between the black hole and the planet. And using that and the known masses, we were able to calculate the forces. And then from there, we were able to rearrange the equation to then figure out what the mass of the black hole was. And averaging all of those data points off, you get 7.735 times 10 to the 43rd. As for part two of the experiment, we started off with the planet in the middle, and you can change around the velocity of the rocket, and the only two forces that are acting on it here are from the moon and from the planet, and so that is how you get different orbits. And you need to calculate both of those and change it every single time to accurately calculate to see if it's going to crash into the moon or not. Here you can see that the rocket ship started off on the moon and orbited around before kind of flinging off before returning, though the month ended before that could actually happen. So for sources of error, we approximated, and we used it because this is a simulation and we didn't necessarily have much time to be able to calculate everything that we needed to. So some things were assumed, such as no external forces on the system, which could mean other celestial bodies imposing a force of gravity. And this could affect the velocities and thus the position, and to and other assumptions like that everything is round, which is not necessarily true. So the radiuses aren't necessarily completely the same, and the masses aren't distributed correctly. And for accuracy, we used trial and error to find the velocities for the figure-8, but we couldn't. So there might be a perfect velocity that could work, but I was unable to find this, and that means the initial variables could have been more precise for this experiment. So as for the additional questions, mathematically, the parallel and perpendicular components of the net force are the same as the parallel and perpendicular components of the rate of change of motion. However, the momentum is a lot easier to calculate because you only need change of velocity. While for net force, you need all of the forces acting in the system. And then for the second question on if the imaginary system had a black hole, a star, a planet, and a moon, what would you need to include to predict the motion of the entire system? And would they be contributing equally? And I said that you need to consider all the parts of the surroundings that are acting on your system and all the parts in the system acting on the surroundings. and that there would be dominant forces that were based on the mass and gravitation. So you could assume that the black hole, because black holes are so massive, it would probably have some of the most impactful gravitational forces. Thank you.